or 2 minutes and
Yeah.
or maybe we could start. Okay. So today we have the pleasure to listen to Dominique Manchon from Université Clermont, Auvergne. And we'll talk about Parsley algebras, post groups, and Gavrilov's K-map.
Okay, so good afternoon and good evening to everybody, and thank you very much for your invitation. So yeah, it's a joint work with several people. Sorry. Yeah, here we go. So joint work with Mahdi Al-Kaabi from Baghdad in Iraq, Kurush Ebrahimi-Fard from NTNU in Norway, Hans Muntekos from Bergen, and Yuan Chang from Henan University in China. Okay, so let me start with a little bit of differential geometry. So it's not new stuff. You can find it in the book by Kobayashi and Nomitsu, for example. But then we'll go to Postli algebra via this route from differential geometry, and then I'll speak about post groups. Okay, so you start with a smooth manifold, big M, and Km will be the space of vector fields on M. And what is an affine connection? It is you can understand it as a covariant derivative operator. So you want to differentiate one vector field in the direction of another one. So to two vector fields x and y, you associate nabla xy. And it is linear with respect to C-infinity maps with respect to the first variable. Nabla fxy is equal to f nabla xy for any C-infinity map f. But nabla x of fy, it is not the case because you have a Leibniz rule. You have two terms. So the first term is f nabla xy, but the second term, you have to differentiate f in the direction of x and then multiply by y. And I jump to a more algebraic notation. I flip the triangle by 90 degrees, and x triangle y will be nabla xy in my notation. Of course, the vector fields are endowed with so-called Lie-Jacobi bracket. It is just the bracket of these two maps because, well, yes, let me recall that the vector field is nothing but a derivation of the algebra of C-infinity maps. And the Lie bracket of two derivations is still a derivation, so it's still a vector field. So now the space of vector fields is endowed with two laws, two binary products, the triangle, which has a priori no property, and the Lie bracket. So Alexei Gavrilov names this kind of structures a framed Lie algebra. So you don't have any compatibility between the triangle and the bracket a priori. Okay. Well, of course, I already told about this, that the vector fields are a module over the ring of C-infinity maps. Okay, no compatibility between the two products. And then, as usual, we can define the torsion by this formula here. X triangle y minus y triangle x minus the Jacobi bracket. And the curvature involves three vector fields, and it's defined like this. X triangle y triangle z minus y triangle x triangle z minus the Jacobi bracket xy triangle z. And these two quantities are very important because both are C-infinity of M linear with respect to both arguments for the torsion and three arguments for the curvature. which is not the case for the triangle or for the bracket. But these combinations happen to be linear with respect to the C-infinity maps. And then you can in some way compose these two quantities in an operatic way to get some more complicated expressions. For example, this one, they are called special polynomials in Gavrilov's work, for example. Okay. I should mention what is X triangle R here. I can differentiate the curvature of the torsion in the direction of another vector field. So I'll go to this in a while. And these derived torsions or curvature are still C infinity of M linear with respect to the arguments. And between curvature and torsion, you have the so-called Bianchi identities. So the first Bianchi identity is written like this. So this integral just stands for circular permutation sum. So in each of these terms, you have a sum of 3 terms if you want. Okay, and then the first identity expresses the curvature in terms of the torsion of its derivative. And the derivative of the torsion, you can see the definition here. It is just a matter of applying the Leibniz rule once again. Suppose you are interested in this term. You want the derivative of the torsion T of yz with respect to x. So you differentiate 3 terms, T, Y, and Z. And so if you apply a Leibniz rule, you will have 3 terms. And this gives you the definition, the very definition of what is the derivation of the torsion in direction of x applied to y and z. So then you have this term minus 2 corrective terms here. The second Bianchi identity involves the derivative of the curvature, sorry, in terms of curvature and torsion. And again, the derivative of the curvature is defined by an analogous formula here, involving 4 terms. Okay. So now I go to specific examples. I suppose that my manifold is endowed with a connection which has no torsion and no curvature. And then you have the so-called left Preely identity. So you have this equation there. That means that the triangle may be not associative, but it's weakly associative in the sense that the associator, maybe it's not 0, but it is symmetric with respect to the first variables here, x and y. So the notion of Preely algebra dates back independently from Winberg and Gerstenhaber in 1963. But the prehistory of this notion can be traced back to Cayley 1 century before. Okay. The next example will be flat constant torsion. So you suppose that you have no curvature. You may have torsion, but the derivative of the torsion vanishes for any x here. Then, if you look at the Bianchi identities, they boil down to so-called Postly algebra axioms. So Postly algebra is a notion invented by Bruno Valette 15 years ago, or a bit more now. And a very close notion of D-algebra was invented by Muntekos and Wright 1 year later. And in particular, the vector fields do form a Postly algebra, and the differential operators do form what is called D-algebra. Okay, so what is a Postly algebra? here are the axioms. First of all, the first axiom is quite natural. That means that the triangle distributes over the bracket like this. So again, a kind of Leibniz rule. The second axiom is more involved. What happens if you triangle a bracket AB on C? So the right-hand side, it is just what I would call the preliator of A, B, and C. That means, okay, we have seen the preli identity there, and the difference between the two terms here is exactly the right-hand side of the second postly axiom. Okay, so in other words, a postly algebra with vanishing bracket is just a preli algebra, because now the first axiom is empty, and the second axiom boils down to the preli identity for the triangle. Okay, so once you have a postly algebra, you can build up a secondly bracket from the first one in the triangle. Here is the formula. And it is a nice, funny exercise to check the Jacobi identity for the Grossman-Larson bracket. When we have a postly algebra, we have an opposite one. So you just put a minus sign before the bracket, and you replace the triangle by the black triangle defined like this. And you can check that both structures share the same Grossman-Larson Lie bracket. Okay, so now there's a more recent notion of post-Hopf algebras. So in a nutshell, post-Hopf algebras are kind of good D algebras. Every post-Hopf algebra is a D algebra. The converse may be not true. Okay, so this notion is due to Li, Sheng, and Tang 2 years ago. In particular, the enveloping algebra of a post-Lie algebra is a D algebra, and it's a post-Hopf algebra. So a post-Hopf algebra is a co-commutative Hopf algebra here, together with a linear map triangle from H tensor H into H, fulfilling axioms which are quite close to post-Lie axioms. So first of all, you have a Leibniz rule for the triangle, but for the Hopf algebra version of the Leibniz rule, okay? So here, the right-hand side invokes the coproduct delta here. This is Swidler's notation for this coproduct. And here, the double triangle here, it is U star V triangle W. And what is this star? It is defined like this. And it turns out to be an associative product, which is so-called the Grossman-Larson product of your Hopf algebra. And there's a third axiom, which is, roughly speaking, the existence of an inverse. Okay. Okay, so in a post-Hopf algebra, you have two Hopf algebra structures, H dot and H star. Both are co-commutative Hopf algebras, maybe not isomorphic. There's no reason they are isomorphic. The antipodes are different, S and S star, but you can get the second antipode from the first one by means of this formula here. And from the Grossman-Larson product of the enveloping algebra, you recover the Grossman-Larson bracket of the Lie algebra, as we can expect. And the first product of the post-Hopf algebra can be recovered from the second one by this formula here, implying the star antipode. Okay. So let me now give an example of post-Lie algebra. the free Postli algebra generated by a magmatic algebra. So it is a construction due to Loïc Foissy a couple of years ago. You start with a magmatic algebra. That means that you have a vector space together with a binary product, which is bilinear, but nothing more. And you look at G, which is the free Lie algebra generated by V. And then you extend the bilinear map triangle from G to this free, the bilinear map, you extended it from V to G by forcing both Postli axioms to be true. So it's very natural. And a particular instance of this example is when you start with some color set V, and you look at the free Postli algebra generated by C, which will be the free Lie algebra over the free magmatic algebra generated by by your set. Okay, and it is given by the formal iterated brackets of planar rooted trees decorated by the set C. And the triangle map is given by left grafting. So let me give an example here. You graph this first tree and this second by grafting the first tree and the second everywhere you can, and keeping the branch on the left. Okay. So if you do this with non-planar rooted trees, as you know, you get the free pre-Lie algebra. But because your trees are planar, it's not pre-Lie anymore. It is purely magmatic. It is, it is the free magmatic algebra generated by your decoration set C. And then you look at the formal Lie brackets of those. And this is the free Postli algebra generated by C. Okay. And if you look at the universal enveloping algebra of this free Postli algebra, you get the free D algebra, which is also a post-Hopf algebra, and it is given by planar rooted forests decorated by C. Okay. Okay, so now another ingredient of my talk will be Gavrilov's K-map. So from Alexei Gavrilov from Novosibirsk. So let me start now with the vector space V, and I look at the tensor algebra T of V. And I suppose that my V is a magmatic algebra, so you have a triangle, okay, a bilinear product. And then I want to define a map big K from TV onto TV. So it's a recursive definition. It is the identity on the unit and on the vector space V. And now it's an induction on the length of the word, and K of x1 tensor, etc., xn will be x1 tensor K of this word of length n minus 1, minus this sum of terms. And this term is also of length n minus 1 because I have contracted the letters 1 and j, and I apply big K to this. So once again, the definition is recursive. As an example, on a word with two letters, x tensor y, I get x tensor y minus x triangle y. And for three letters, I get sum of 6 terms with alternate signs, and I get the word itself plus or minus corrective terms of strictly smaller length, right? So as a result, it's obviously a linear isomorphism because it's a kind of deformation of the identity. K of a word is equal to the word itself plus some corrective terms of smaller length. Okay. Maybe the inverse is even more interesting because we do have a non-recursive expression for the inverse. So K inverse of a word of length n is a sum over all the partitions of the set 1 up to n of terms depending on the block. No, sorry, the terms indexed by the partition is the length of the partition, so the number of blocks. And so each term of this word, each term YB is an iterated triangle of the letters composing the block, okay? And you form your word, you form your expression by iterating the triangle and putting the parenthesis on the right, like this. And in the word here, you order the blocks with respect to their maximum. So, as an example, k minus 1 of x tensor y is equal to x tensor y plus x triangle y, corresponding to both partitions. Here, the partitions with singletons, and here, the trivial partition with a single block. And for a word of length 3, I get 5 terms because you have 5 partitions of a set of cardinality 3. And you remark that you don't have any alternating signs anymore. Okay, so it's an important result by Gavrilov that this K is a Hopf algebra isomorphism from T of V star onto T of V dot. So let me stress an important point there. So T of V endowed with all this structure is a post-Hopf algebra, okay? And in that particular case, both Hopf algebra structures are isomorphic. But it is very particular to that situation because in a post-Hopf algebra in general, once again, both Hopf algebras are not isomorphic. But here they are. And we have an explicit expression of Hopf algebra isomorphism between both structures. So in particular, if you restrict to the free post-Lie algebra, you get a Lie algebra isomorphism between both Lie structures. Okay, so now I give an old example of post-Lie algebra dating back from Müntefos and Wright in 2008. So I go back to a smooth manifold with a smooth right action of a Lie group big G on it. So it's an example of manifold with a connection with flat, which is flat and with constant torsion. And let small g be the Lie algebra of big G, and small gm, which will be the infinity maps from M into G. So it's a consequence of Müntefos and Wright's work that Gm is a post-Lie algebra. So the Lie bracket is just the pointwise Lie bracket, x bracket y at point x in M. It's just big X of x and big Y of x, the bracket of these in the Lie algebra G. And the action, x triangle Y, it is built up as follows. Any sin infinity map from M into small g induces a vector field on M. I denote it by sharp x. And then I let this vector field sharp x act on the map Y. Okay? And it gives you another map in sin infinity of M with values in G. And I evaluate this map at point small x. And it turns out that with both triangle and bracket, you get post-Lie algebra. And the corresponding Grossman-Arson bracket reflects the Lie-Jacobi bracket of vector fields. So this is this formula there. Okay. So if the action is transitive, any smooth vector field is equal to some sharp x, maybe not unique. If not, you just recover vector fields which are tangential to the orbits of the action. Okay, so now I come to post groups. So post groups are a very recent notion dating back from last year by Chengming Bai, Li Guo, Yung-Hei Sheng, sorry, and Rong Tang. So what is a post group? It is a group endowed with a further triangle map, and so that first of all, the right translations by the triangle, the left translation by the triangle is a group automorphism for any A in G. So sorry, it should be a small a there. It's a typo. And first of all, A acting on B acting on C, it is just A star B acting on C, with A star B by definition is A dot A triangle B. Okay, so these are the axioms of a post group. So it turns out that G endowed with this new star is also a group. We have called it the Grossman-Larson group, and it shares the same unit with the group you started with. And G star acts on G dot by automorphisms thanks to the triangle. Okay, so if you ask me how did the authors coin this definition, you just go to post-Hopf algebras and you look at group-like elements inside this post-Hopf algebra, and you notice that you have two group structures on it, the star and the dot, and the triangle, and then you very naturally end up with these axioms. So it's a very natural notion. So now we can define the notion of opposite postgroup. So you reverse the multiplication and you replace the white triangle with the black triangle, which is just the white triangle twisted by the conjugation by A, like this. And both groups share the same Grossman-Larson group structure. Okay. So the four authors noticed that if you differentiate so-called a post-Lie group, you will get a post-Lie algebra. So you differentiate twice the action of you differentiate twice the triangle of a post group like this, and you get that the Lie algebra of a post-Lie group is a post-Lie algebra. And both notions of opposite coincide. So that's what we noticed with Madi and Kurush. And now I come to this very important theorem by Guo, Sheng, and Tang, noticing that the notion of post-group is in fact equivalent to two older notions. First of all, the notion of skew-brace due to Guarneri and Vendramin in 2017. And it's also equivalent to the notion of braided group by Lu, Yan, and Chu in 2000. So I'll give a brief account of this because it's important. So what is a skew brace? So it is just a set endowed with two group multiplications, dot and star, and such that you have this compatibility between the star and the dot. So here the inverse is respect to the dot. And if you have this, if you denote by E the unit for the first group multiplication, it's very easy to see that you get that E is also the unit for the second multiplication. You just put B equal to C equal to E in the axiom there, and you get very easily that A star E is equal to E star A is equal to A. Okay, so And now you define the triangle like this. A triangle B is equal to A inverse dot A star B. And then G dot and triangle will be a post group. And conversely, if you start with a post group, you get a skew brace G dot and star is nothing but the Grossman-Larson product. So both notions are equivalent in a quite easy way. You can easily convince yourself. For braided groups, it's a bit more surprising, I guess, and less direct. But let me stress that Guarnieri and Vendramin noticed that skew braces are closely related to set theoretical solutions of the Young-Baxter equation, and so are also braided groups. So it's quite natural to seek relationships between both notions, and in fact, they are equivalent. So what is a braided group? So from a Lu, Yan, and Chu paper, it's a triple GM sigma.
Dominique, I have a small
Yes,
question.
yeah, sure.
In the theorem, you say that they show that post groups are equivalent to braid groups and the previous groups I don't remember. But
Yes.
those the connections between braid groups and the groups that you presented before were made at some point?
Between braided group and which groups? Post groups or
And the skew brace group, yes.
yes, sure. Because yeah, I could say first of all, skew braces and post groups are equivalent notions. Now we know that, and
Yes.
The four authors of the first post group papers showed that braided groups and post groups are also equivalent notions. So
Okay.
all these three notions are really the same. And now let me explain in a nutshell why braided groups and post groups are equivalent. So a braided group is a triple, GM sigma. So GM is a group, so M is the multiplication of your group. And sigma is it's a braiding, so it's a bijection from G cross G onto G cross G, so that you have this you have two compatibilities. First of all, sigma composed with M cross M is equal to M cross M composed with a guy called sigma tilde. Sigma tilde is given there. So it goes from G to the 4 to G to the 4. And the second condition is a braided commutativity axiom. M composed with sigma is equal to M. So how to understand this graphically? So M composed with sigma is equal to M is graphically it is drawn there. So if you flip both entries with sigma and then multiply, it is the same than directly multiplying. And sigma tilde is the double braiding, which is drawn there. Okay, so you braid like this. Okay, and then graphically you understand what this condition means. Okay. So the properties which are proven in the Lu Yan-Chu paper from 2000 is that sigma is indeed a braiding. It verifies the braid equation. So the graphical picture of the braid equation is there. It is the third Reidemeister move for topologists. Okay. As a consequence, big R is equal to flip composed with sigma verifies the set theoretical Young-Baxter equation, which is written there. And the flip, it is just exchanging both coordinates. So it's what is called also the trivial braiding. Okay. So let me stress that if you flip and flip again, you get the identity. So this is involutive. But if you use a braiding, in general, a braiding is not involutive. If you braid twice, you don't have the trivial map. You don't have the identity in general. Okay. So now let me introduce the notation sigma of xy is equal to x acting on y and x on which y acts. Okay. And both maps say left harpoon and right harpoon are respectively on left and the right action on G on itself. So it's also from Lu Yuanchu. Okay. And then start from a post group. Then the Grossman-Larson is braided. And the braiding sigma is given by this. So the left leg is given just by G triangle H. And the right leg is given by this expression. Conversely, starting from a braided group G star and sigma, so you write down sigma like this, and then you get a post group G dot triangle, whose Grossman-Larson product is the star, and explicitly the triangle is just given by the left harpoon of your braiding, okay? And the dot is given by this expression in terms of the star and the left harpoon. Okay. So one of our results is just direct verification. It's not extremely difficult. We noticed that the braiding corresponding to the opposite post group is just the opposite of the braiding. So as a consequence, what we call the pre-group, it is the same as a symmetric braided group. And what is a pre-group? It is just a post group in which the dot product is commutative. So a pre-group is an abelian post group, if you want. And then pre-groups are associated with braidings which are involutive, I mean. Okay. Okay, so now maybe more involved of our results. We got a weak post group from group actions. So you consider a set M, you consider a group right acting on it with unit E, and G to the M would be the set of maps from M into G. So it is a group under the pointwise product. F dot G evaluated at X it is f of X multiplied by G of X. So the unit will be the constant function equal to E, of course. And you have another binary product, the triangle, given by F triangle G applied to X is equal to G evaluated at X on which f of X acts. Okay, so think about it. It gives you an action and maps F triangle something are group morphisms. It's quite easy to check. So it's not exactly a post group, unfortunately, because these triangles F triangle something, they might be not group isomorphisms. But you have a big subsets which forms a group acting on Gn dot with automorphisms. So the notion of weak post group is due to Shukung Wang on an archive paper in July 2023, and that's exactly the notion we needed. And it turns out, okay. I should make a remark. I was aware very recently that this weak post group comes from a structure of what is called a post groupoid by Sheng, Tang, and Chu. So Yun-Hei Sheng was nice enough to share this very new result with me. So I just mentioned this. It seems to be a very promising direction. Okay. So now we look at the smooth version of this. Now M is a smooth manifold, G is a Lie group with Lie algebra, and G to the M is a set of smooth map from M into G. So with some quotation marks, because you look at the weak post group G to the big M, it turns out to be a weak post Lie group. Of course, it's infinite dimensional, but in some sense, it's a post Lie group. And if you differentiate twice like this, you get the post Lie algebra I told you before, big G to the M. Okay. So that's one of our results. And now to finish my talk, I'll go back to abstract post groups. And we wanted to sort out the notion of free post group. So it's a bit involved because if you start with the magma, it's not clear what is the free post group generated by it. You can generate a post group from some special magmas, which we call the left regular diagonal. So a magma M triangle, so it's a set with a binary product, and it is left regular diagonal whenever two conditions hold. First of all, the left translations are bijective, and secondly, this map big lambda, given by lambda of A is equal to the inverse of the translation by A applied to A. This map big lambda is bijective. So this technical condition is necessary. And our main result is this one. For any left regular diagonal magma M, the free post group generated by this magma M is a post group. And it fulfills the universal property here. That means that for any post group G dot triangle, for any map phi from M to G dot triangle respecting the triangles, there is a unique map phi tilde extending the map phi, which is a post group morphism. Okay. More precisely, this map phi tilde, you use the universal property of a free group to say, okay, my phi tilde is a group morphism, but it turns out that it also respects the triangles there, and it turns out to be a post group morphism. And secondly, there exists a unique explicit group isomorphism, big J, from the Fm with the dot onto the Fm with the Grossman-Larson product, which extends the identity of M. And its even inverse K from Fm star to Fm dot can be seen as a post-group analog of Gavrilov's K-map. Okay, so here are some references. So our two papers on which this talk is built. The paper by the four Chinese authors on post groups. The paper by Guarnieri and Vendramin on this. The paper by Li, Sheng and Tang on post-Hopf algebras. And the paper by Lu, Yan and Chu on braided groups. And thank you very much for your attention.
Okay, thanks, Dominique, for your nice talk. Are there any questions in the audience?
Yeah, I do have a question.
Yeah, please.
Thank you for this nice talk. Can you go back to this last commutative diagram? This phi needs to respect triangle.
This result, yes. Okay, so
I'm asking, does it need to respect triangle phi?
Sorry, can you ask it again? I didn't get your point, please.
So I'm asking that does phi need to be linear in triangle?
Finite?
Phi is just a set map, or it needs to respect the triangle?
Okay. The map phi. First of all, it must respect the triangle. So you start with a map phi, a magma map from M triangle to G triangle. Okay, and then and then you go to the free group generated by M. So you build up the phi tilde, which will be a group morphism from FM.
That's great. I understand. Only those maps could be extended which respects the triangle, like to the free group.
Yeah. But then
So like these are the free objects in this category. These are the free. This condition seems to be a little bit weak as usual. Like, because in usual every set map could be extended to a morphism in that category.
Yeah. So yes, the result is that your phi tilde isomorphism is in the morphism.
Isomorphism category of post groups.
No, it's not an isomorphism, but it is a homomorphism in the category of post groups. That's the result.
So no, I'm asking, are the free objects in this category?
Are there
free objects in this category?
Free objects in these categories. No, because no, I don't think so, because I started with the magma. And if you start with a set, even with a set with only one element, what is the left regular diagonal magma generated by a set of generators? It's already a huge thing. So in some sense, we don't really get the notion of free post group generated by a set.
One more question.
Yeah.
So like there's this concept of free skew-braces. So are they related to with this? Like, of course, this you can define a free skew-brace structure over FM.
Okay, there's a notion of free skew-brace. Okay.
Yeah, I'm asking, is there any connection with free skew-braces?
Okay, so this I don't know. I have to check this.
Okay.
Yeah. Sorry for that. Yeah. But if there is a notion of free skew-brace in the literature, I have to check and compare with this notion there. Sure.
Yeah. Thank you.
There are other questions or remarks? Yes, Dominique, I have a kind of very broad questions, because this kind of notion of post-group really appeared recently, and is inspired from, it's connected to postly algebra, which were used in the context of numerical analysis. What this perspective on post-group could bring, for instance, to a field like numerical analysis for Lie-Butcher series?
Okay, so
it's kind of vague, but
yeah. So once you have post-Lie algebras somewhere, you have post groups, and you know that post-Lie algebras appear, for example, in the recent multi-index B series or this kind of structures.
Yes.
So this is a first approach. A second approach will be if in regularity structures you use non-planar trees.
Yes.
If you go to planar versions, then of course you have plenty of postly algebras there, and then naturally the notion of postgroup is there.
Yeah.
So maybe I don't have more precise answers from now on, but I'm quite sure they will appear. Yes.
No, for sure. I think one could
Yeah.
identify a postgroup in this context. What are the specific postgroup in this context?
Yeah.
But it was more like a vague questions, what I can bring into, for instance, the analysis or the solutions for these equations, or the understanding of the series that I'm using. Having this information, knowing these informations. But it's kind of vague because I clearly don't have the answer.
Yeah. But of course, the groups appear as renormalization groups in analysis and probability to get true solutions of your ill-posed equations in some way. Are these groups post groups? From now on, I don't know. I don't think so, but they could also appear in this context.
Okay.
And I would also share with you a very, very broad question. Of course, people are really interested in representations of groups, representations, characters, etc.
Yeah.
Is there a notion of representation for a post group? That would be very interesting.
Okay. So maybe someone in the audience have an idea, maybe not.
Yeah.
Are there other questions or remarks for Dominique? Just turning back to the audience. Doesn't seem the case. In that case, I just would like to thank again Dominique for your talk. Very nice.
Okay. Thanks very much for your invitation once again.
Yeah, I mean, I'm just a chairman, but I'm just going to thank Joe Beer and the other organizer. That's nice. Okay, so I think we can close the session now. Thank you for being there.
Okay, bye. Thanks a lot.
Bye.